You're here because you want to master chemical bonding with a University of Cambridge graduate. You can start by going to the link below and download my notes, and then sit down and run through the notes with me as I give a lecture on it. Let's begin. So when we look at chemical bonding, right, we start to put together the picture of atoms coming together to form different kinds of compounds and molecules, and what are the kinds of bonding and the structures that you can form with the different atoms itself. Do take note that chemical bonding may look like one of those very memorizing heavy kind of subjects, but actually with the right understanding and being able to know how to apply the various knowledge for chemical bonding, we will be able to navigate this without really memorizing too much. Now, before I go through the content, just take note that we always have these learning outcomes available, and I'll be referencing to them throughout the lecture. So let's start off by defining what exactly is a covalent bond. Covalent bonds are electrostatic forces of attraction, right, between a shared pair of electron and positively charged nuclei. So you have learned this previously in secondary school, but essentially this is the sharing of electrons that forms the bond between atoms. But what exactly is the sharing of electrons and how is it done? Well, these atoms would share electrons through overlapping of the valence orbitals. And here we can see an example. So remember how we learned about atomic orbitals back in the atomic structure chapter. When you overlap two orbitals together, so let's say we have an atom of Al and an atom of chlorine, and when we try to overlap the orbitals together, that's how the bonds, specifically the covalent bond, is formed. So here you can see a typical example of a SS orbital overlap. And just take note that the nucleus to nucleus distance between the two atoms is what we generally define as the bond length. Now moving on to sigma bonds. So sigma bonds generally are formed due to head-on overlap of the two orbitals. So we can see some examples where that you can have a SS orbital overlap or SP or a PP orbital overlap, and these are in general some of the more classic and normal overlaps that we see. But when we move on to a pi bond, pi bonds are classified by their sideway overlap, and they generally involve p orbitals, right? So an example of this is in this diagram over here. You can see that the side-on overlap kind of is a little bit more awkward, but it will overlap. And one thing to take note is that the head-on overlap generally has more area of coverage versus the side-on overlap. So this side-on overlap tends to be weaker, right, than a head-on overlap, aka a sigma bond, right? Now, this is quite important when we move into types of covalent bonds. So we already know before that atoms can do multiple bonding, whether it's double bonds or triple bonds, and you realize that they always consist of at least one sigma bond. Sorry, not at least one, but only one sigma bond. And then afterwards, they will have the pi bonds on top of it. And why I bring up the fact that the side-on overlap is weaker, because in general, within the whole double bond, not all the bonds are of equal strength. You will see that this tends to be stronger within the same molecule compared to this one over here, the pi bond, right? Now we move on to dative and coordinate bonding. So this is a new term that is brought up in JC, and please take note that they really love to test this. So what is dative or coordinate bonding? Dative bonding is where one atom provides both the electrons in the whole sharing relationship instead of both atoms sharing equally. So what do I mean by that is the donor atom provides both the electrons. This usually comes from a lone pair, and the acceptor atom must contain an empty valence orbital. And this makes sense because the lone pair needs to have a space to go into the acceptor atom itself. So an example is chlorine and aluminium, and this generally is seen in aluminium chloride, because aluminium tends to be electron deficient in that molecule. So it has that empty valence orbital that accepts the lone pair from a neighboring chlorine atom. I will get more to that in the next few pages. Another thing to take note is that native bonds have the same strength as covalent bonds. So don't just treat it any specially from a covalent bond just because it acts a little bit differently. Now we move on to electronegativity. So electronegativity, please memorize this definition. Exams love to ask this. And what is electronegativity? This is the ability of an atom to attract the shared pair of electrons in a covalent bond. So what does it mean? It means that generally in a covalent bond over here, right? Let's say Al and Cl, right? We look at who is more electronegative, and you would think that the electrons tend to stay in the middle, let's say over here. But in reality, because chlorine is more electronegative, it pulls the electrons towards this way more, right? So you can imagine it like I always liken it to like a magnetic force, a pulling force basically. But because chlorine is stronger than aluminium, the electrons tend to be somewhere around here. And what does this depend on? Well, it depends on the nuclear charge and the distance of the outer electron from the nucleus. In general, when I want to find out what is the rough electronegativity and compare it between atoms, I will look at the periodic table, and the trend is if it's more to the right and it's more to the top of the periodic table, right, means that it has a higher electronegativity. So an example would be O versus N, right? If you look at the periodic table, O is more to the right of N, so this is more electronegative. And now I'll come to why electronegativity is important to understand later on as we go through chemical bonding. And I'll get to why electronegativity is so important to understand. Well, it's important because you needed to understand what is bond polarity. Bond polarity is when you have a bond and the two atoms involved, both of which have different electronegativities. And because of this, there's a unequal sharing of the bonding electrons. Kind of like how I described aluminium and chlorine just now. Now, because of this, there's this term here which is a dipole that starts to exist between the two atoms. A dipole is basically the unequal sharing of the two electrons. Now, the strength of the dipole, or perhaps the magnitude of the polarity, as to no one's surprise, is due to the difference in electronegativity. So the greater the difference in electronegativity, the greater the magnitude of the polarity. And here we have an example with hydrogen and chlorine. So because chlorine is more electronegative than hydrogen, I like to draw this delta minus over here on the more electronegative atom and the delta plus on the less electronegative atom involved in the bond, right? And when questions ask you to draw the polarity or draw the dipole moment, you have to draw this little arrow over here and with the dash downwards or perpendicular to the arrow. Now we move on to bond strength. So bond strength is measured by the bond energy. And bond energy is, yes, you have to memorize this definition. And bond energy is the amount of energy required to break 1 mole of covalent bonds in that gaseous state. An example is when we have bromine gas, so there would be this Br bond over here, and I'm just breaking it. And specifically, it needs to be in the gaseous state. So the bond energy is a good gauge of the bond strength, right? And just in general, it's good to note that energy is released during bond formation. I should use a red pen here. And energy is absorbed during bond breaking, right? And the strength of my covalent bond is dependent on a few factors. One is bond order. The other is effectiveness of overlap of orbitals. And the other one is bond polarity. So going to each of them, bond order means if there's more bonds, there's a greater strength. And this kind of makes sense because when you have more bonds, means you have to break each and every single one of the pi bonds and also the sigma bond, which will be there. And the more bonds you have to break, it generally means that you need more energy. Next is effectiveness of overlap of the orbitals. So when you have larger orbitals, they tend to be more diffused and there is really less effective overlap. You can think of it like the surface area of overlap or the surface area of contact between the two orbitals. And I know this is a bit hard to visualize, so I have a little diagram over here where you can see that in a 3s orbital, 3s tends to be bigger than the 2s, right? And while it does look like this area of overlap is about the same, but as an overall, you can think of it like an overall percentage wise, right? This has lesser overlap. But we don't really call it lesser overlap, we call it more less effective overlap compared to 2s over here. So you can think of it kind of like the percentage. Right? So a key answering technique whenever you're asked about why a certain bond is weaker or stronger than another bond, it would be that you want to talk about the valence orbitals, right? So they tend to be bigger or more diffuse, and therefore there is more or less effective overlap of the orbitals. And therefore you conclude based on the context of the question. So it could be that there is a stronger bond or a weaker bond. So the next factor is bond polarity. So with no surprise, it's when a bond is more polar, it tends to be stronger. And this is because when you have a delta plus and a delta minus, there are additional forces that come into play between the delta plus and the delta minus, these partial charges, and they help to strengthen the covalent bond. So just take note of this. And another important thing to take note is the bond length. So bond length is kind of a gauge to also how strong a bond is. In general, a bond is longer would mean that the bond is weaker. And this is kind of in line with like the whole overlap. So if you see over here, bond length is the distance between the two nuclei of the two atoms, right? So if you look at this length over here, if it's longer, means the orbitals are more diffused, means there's also less effective overlap over here, and the bond is weaker, right? So when you put in all the factors together, higher bond order, higher polarity of the bond equals the bond length will decrease. And this means the bond strength is higher. And you can flip this around if you're talking about a weaker bond. Alright, next part is I want to go through with you how to draw my dot and cross diagrams. This is a very common question in the A-levels, and you should be expected to understand and draw very fast how to identify the dot and cross of any molecule or of any compound, right? So things to take note is there is only valence electrons that you need to draw, and then how you want to go about it is you want to look at what is the central atom, right? So something with very low electronegativity, that's one way to go about it. And then note the number of valence electrons. And what I want to do, right, is I want to try and fulfill the stable configuration of every atom around. So when it comes to period 2 elements or lower, I want to make sure that it is an octet structure, right? When it comes to period 3 and above, then because they can use d orbitals for bonding, do take note of this because they love to ask this part as well, they can go above 8 valence electrons. But in general, it is a good bet to try and make everything have 8 valence electrons, right? And how you would do this is you try to figure out which atoms need how many bonds, right? So for example, if you have an N atom, you know that N has 5 valence electrons, right? And in order to get 8 valence electrons, it needs 3. So it needs 3 single bonds. So you can get 3 more electrons from all the sharing. Or it needs like 1 double bond plus 1 single bond. Or it needs a triple bond, right? So you'll go around and figure this all out, right? And of course, the rest of the electrons are lone pairs. Now we will move on to something that is more unique to the JC syllabus. I'm talking about shapes and my polarity. So shapes of molecules are generally determined by the number of bond pairs and the number of lone pairs, plus some additional rules. Here we have this theory called the VSEPR theory, and the VSEPR theory stands for the valence shell electron pair repulsion theory. It consists of 2 rules. One is electron pairs must be arranged around the central atom as far as possible. So if I have an atom, I want to arrange the electron pairs like this and not like this. This is because electron pairs are all negatively charged and they generally want to repel each other to the maximum and stay as far away from each other as possible so that they are more stable. Next up, rule number 2 is that the lone pair repulsion is greater than the lone pair bond pair repulsion and is greater than the bond pair repulsion. So a good rule of thumb is lone pairs tend to repel much more than the bond pairs. So we have a table over here that summarizes how to determine the shape of a molecule. So as I said just now, that you want to go by the number of bond pairs and the number of lone pairs. And from there, you figure out the shape itself. And the number of bond pairs and the number of lone pairs, you can tell the shape because it is guided by how the electrons tend to move or arrange themselves around the molecule, right, to get this electron pair geometry. So what do I mean by that? Well, let's just go down the list slowly. So when you have 2 electron pairs, well, obviously they will want to arrange themselves as far away as possible, so they will be linear, right? The furthest away is when the bond angle is 180 degrees and they're just at opposite ends of each other. Okay, now how about when you have 3 electron pairs? So when you have 3 electron pairs, the easiest way is through a triangle or a trigonal planar, right? So in this case, you have this and it's a 120 degrees, right? And all the bond angles are equal, so there's no favorites, right? But then when you have 2 bond pairs and 1 lone pair, right? Remember rule number 2, where lone pairs repel more than bond pairs? Well, if that is the case, right, you'll get a structure like this, right, where the lone pair, right, is repelling more than the bond pairs. So it's actually kind of like the selfish big brother of the family that would just shove the younger siblings away. And when they shove the younger siblings away to make more way for themselves, they will occupy more space, and because of that, the younger siblings have to squeeze closer to each other. And because of that, the bond angle will decrease. So when you look at this one, the bond angle will be lesser than what is expected. The expected is 120, so it will be lesser, so it will be about 119 degrees. And when it comes to the shape, right, this is bent. And you're gonna ask me, why is it bent? Well, because when we look at the shape, we don't really look at the lone pair, right? So if I look at the whole molecule without taking into account the lone pair, right, it's just really a bent shape here, right, ignoring the red portion. So do take note of that when you're trying to find out what or how to name the shape of the molecule. Now we go down the list and it starts to become a little bit more 3D. So now it is tetrahedral because there's 4 electron pairs, and in the 3D shape, right, you will have these little symbols over here where the wedges show that it is going towards you, right? So imagine it's going towards you out of the paper, right? So it would just be going towards me if I'm looking at the exam paper, and if it is a hash symbol, it means it's going away from you, right? So in this case, if I'm looking at the exam paper, it's going away from me. And because of this 3D arrangement, all the bond angles are the same. You get a 109.5 degrees. Now when it comes to trigonopyramidal, which is 3 bond pairs, 1 lone pair, right? The angle will decrease. And you can see a pattern where it decreases by 2.5. And then next one is minus 2.5 as well. Right? And we move on to trigonobipyramidal, right? So trigonobipyramidal is, you can imagine it like, this is, why is it called trigonobipyramidal? Because this is essentially a triangle, right? And there's a little thing on top, so they actually form like a pyramid on the top. You can see that, wow, I did really good to draw this. So you form a trigonobipyramidal. So trigonopyramidal means it's a triangle base and it forms a pyramid, and then it also forms downwards as well. So it would form downwards. So you have like 2 trigonal pyramids on top of each other. So that's why it's called trigonobipyramidal. And the angles are, well, if you combine like a trigonoplanar on one plane and then upwards, so it's 120 degrees on the plane, and then on the axis is 90 degrees, right? And then when you have 4 bond pairs and 1 lone pair, this tends to be the seesaw, right? So you imagine putting the lone pair on the side and you get a little seesaw, right? And of course, because of the lone pair pushing the younger siblings, your bond angle tends to be lower than expected. And then when you have 3 bond pairs and 2 lone pairs, you get this T shape, right? And you can see that it actually forms a T, right? And this tends to be about less than 90 degrees, about there. And if it's 2 bond pairs, 3 lone pairs, then, well, you get a linear shape. Again, we only take into account the shape of the bond pairs. You don't really look at the lone pairs. Okay? And this is 180 degrees. And then lastly is octahedral. So when you have 6 electron pairs, this is octahedral, and you can see that it is just kind of like, if you have troubles looking at it, it's kind of like a square bipyramidal. So it's like a square and then there's the axis. So very similar to trigonobipyramidal. And the shape of octahedral is all 90 degrees, right? Now if you look at a square pyramidal, right, it's square pyramidal because the bottom part is just a lone pair, and then it gets a little square over here, right? And of course it's less than 90 degrees in bond angle. And then if you have 2 lone pairs and 4 bond pairs, then the 2 lone pairs will just take up the top, and then you just have a square planar because they're all in the same plane. So you just end up having a square. So I hope this is a very good way to help you memorize this table, right? But if you still have troubles understanding, then of course the only way would be just to memorize. So just take note that you have to memorize the name of the shapes, how to draw the shapes, and also what are all the bond angles. Now next is talking about the polarity of molecules. So remember just now how we talked about dipoles or bonds? Well, when it comes to the polarity of molecules, you have to look overall, accounting for all the dipoles of the bonds to determine if a molecule is polar or non-polar. So for example, over here, when I look at BF3, so this is BF3, I see that the shape is trigonoplanar, right? And because they're all in one plane and all the atoms on the borders, so the fluorines, are the same, so they have the same electronegativity, right? And what they're doing is they're all pooling the electrons within their BF bonds to the same extent. And because of that, you have no net dipole actually, because they're all pooling to the same extent. If you have troubles visualizing this, go ask your physics friend on the side, right? And because of this is non-polar, right? But when you look at NH3, for example, right? So this is NH3, and again, all the atoms on the outside are the same. So this is hydrogen. So N is more electronegative, it's pulling all the electrons. But because of its shape, right? This shape, if you reference above, this is trigonal, pyramidal. So because of that, right, all the H atoms are actually below the N. And in general, it's pulling up the electrons upwards, right? So because of you accounting the shape, you actually realize that NH3 is a polar molecule because it has the overall net dipole. Now, why is identifying the polarity of molecules so important? It's because you have to use it to identify the intermolecular forces of attraction. So intermolecular forces of attraction are categorized into three main forces. One is ID-ID, well, I like to call it dispersion forces. Two is PD-PD, permanent dipole forces of attraction. And three is hydrogen bonding, which is, as the name suggests, the bonding of hydrogen. Well, not in an actual covalent bond, but it really is a very strong force of attraction. So when we look at ID-ID first, this is predominantly found in non-polar molecules, right? And just take note that while I do say it is predominantly found in non-polar molecules, a very common misconception over here, so just take note, is that polar molecules don't have ID-ID. And this is just simply not true, because ID-ID exists in every molecule. It's because you can think of it like the interactions of electron clouds, right? And everything has an electron cloud. So there will be some ID-ID, but in non-polar molecules, it is more predominant than in polar molecules. So the strength of your ID-ID is very dependent on the number of electrons, right? Because as I said, when I talk about electron clouds, right? If I want more interaction, so actually if I want more interaction, I'll need a bigger electron cloud compared to a smaller one, right? And there's a typo over here. Right, so more electrons means greater unsymmetrical distribution of the shared electron cloud. And another factor is looking at the shape of the molecule. So because of this interaction, right, you can think of it like this example over here, where I have two molecules. They actually have the same chemical formula, but just different structures. And so if I zoom in, you can see the structures, and one is more elongated, which is this one at the bottom, my butane. And one is more what they call spherical, right? Or slightly branched. And because of that, right, you can see that the area of interaction, or the area of sort of, they're not really contacting, but they are just mingling around each other. So the area of force between each other, when it's elongated, is actually stronger. Stronger than the spherical one on top. And you can think of it like packing your items, right? It's easier to pack elongated branches of molecules compared to spherical molecules itself, right? So again, look at the greater surface area of interaction. Now next is hydrogen bonding. Hydrogen bonding is predefined by two conditions. So one is that the hydrogen is bonded to a very electronegative NOF. So what this is doing is actually making the hydrogen very hungry. Hungry for what? Hungry for electrons. Right? And condition number two is that the NO or F has to have a available lone pair. Right? And because it has an available lone pair, my very electron hungry hydrogen is going to try and take a bite out of the available lone pair. And you can see over here is that, oh, I have an N, I have an available lone pair right over here. And what it's going to do is that the hydrogen, because there's this delta minus over here, and the delta plus, right? So this hydrogen is very electron hungry already, right? It's taking away, the oxygen is taking away its electrons in the hydrogen. So hydrogen really wants electrons. So you'll go for the nitrogen lone pair. And here, this is typically how we draw the hydrogen bond and label it with all the partial charges. So take note, you have to write all your partial charges and show the lone pairs so I can effectively show the interactions. Now, what is the strength of the hydrogen bonding dependent on? This is dependent on mainly the extensiveness of my hydrogen bonding network. And what does that mean? Well, we are looking at how many hydrogen bonds can a single molecule bond. So if you look at water, a very common example is that water has 2 hydrogens and 2 lone pairs, right? So at every time, one molecule can always do hydrogen bonding to like 2 different water molecules. Well, actually, it's more of like 4 different water molecules because these hydrogens can also bond to, pardon me. So these can also bond to other water. So you can actually bond up to 4. Of course, putting in all my delta minuses and my delta pluses. Right? Now compare that to hydrogen fluoride. So HF on the right, hydrogen fluoride can only bond up to 1 because this F, right, it may have 3 lone pairs, but each HF molecule only has 1 hydrogen, so it can only do it once. And because of that, you will see that water has a much higher boiling point or melting point compared to HF. And secondly, we want to look at the polarity of the bond. So if it is more polar, it is a stronger interaction. Now overall, when I look at all of the intermolecular forces, looking at the strength, hydrogen bond is at the top. Okay, hydrogen bond is very strong. It is actually about 10 times stronger than ID-ID. And then after hydrogen bond is PD-PD, and then after that it is ID-ID. Moving on, we're going to talk more about structure and bonding. And just to take note, a key answering technique you would need, right? So here I would put that this is a answering technique. Right? Whenever you want to answer a structure and bonding question, just follow the following format, which is this particular molecule or compound or atom, right, exists as a whatever structure, right? So you have to find out the structure from the molecule, and it has this main bonding or force or the predominant bonding or force, right? And because of that, you explain with relation to the context, which is usually you would need to demonstrate why it has certain physical or even chemical properties. Now, if we take a look at simple molecular structures, so the main forces are the intermolecular forces, right? So we're talking about ID-ID, PD-PD, and hydrogen bonding. So whenever I answer, I would say that, for example, water exists as a simple molecular structure with, and then I look at the forces. So remember, water can do hydrogen bonding. So it exists as a simple molecular structure with strong hydrogen bonding between the molecules, and therefore, blah, 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 blah. Explain the physical properties. So what are some of the properties of simple molecular structures, right? We're talking about low melting point and boiling point. So in general, it has very low boiling point and melting point because these forces of attraction, the intermolecular forces, are very weak compared to the grand scheme of compounds and ions and whatsoever, right? So little energy is required to overcome. So take note of these answering techniques. This is very good. And then it is also a non-conductor of electricity in any state because your electrons, again, do take note of this answering technique, is that your electrons are localized in your covalent bonds. So because of that, you don't have any roaming electrons or any mobile charge carriers, right? So when we look at conducting electricity, we want to look at mobile charge carriers. So now on to a very important item in chemical bonding, and a new item actually, is solubility. solubility, you have to follow this answering technique. And this technique pretty much explains by itself that you understand the concept. The concept here is that in solubility, you want to create energy that actually is formed from the solute to solvent interaction. If you don't know what's a solute and a solvent, the solute is basically what I'm trying to dissolve. And the solvent is what medium I'm trying to dissolve in. So for example, if I'm trying to dissolve my Milo powder into water, the Milo powder would be the solute and water would be the solvent. Now back to this, the energy created when forming this solute or to solvent interactions, I want this to be large enough so I can compensate the energy required to overcome interactions between the solute-solute interactions and the solvent-solvent interactions. Right? And oops, I should highlight this part. And this makes sense because, right, you can't really form new interactions until I overcome the interactions within itself, right? And you should turn this explanation around when you are also trying to say when a solid is not really soluble in a solvent, okay? And how do you find this solute to solvent interaction? Well, you have to look at the polarity, right? So when I look at the polarity, right, if I'm trying to see that bromine is actually soluble in hexane, for example, so this is the solvent and this is the solute, right? And both are non-polar molecules, so they would form very favorable dispersion forces between each other. And because you form favorable dispersion forces between each other, it will produce enough energy to overcome the interactions within the bromine, which is the solute-solute interaction, and the hexane, which is the solvent-solvent interaction. And you look at the other way, is that I2 is not very soluble in water, right? Because I2 is non-polar, and water is very, very polar. And because of that, you form very non-favorable interactions. You actually form this thing called PDID, which is permanent dipole-induced dipole interactions. These are very weak, okay? Very, very weak. Weaker than IDID. And because of that, the energy formed from this new interaction is not enough to compensate the interactions within itself, right? We're talking about the dispersion, the IDID in I2 and the hydrogen bonding in water, which are very strong. And because of that, your I2 tends to not be soluble in water. Now moving on to dimerization. So dimerization is usually detected when you have two molecules that bond to each other in a certain way or form very strong and compatible forces of interaction. And you can tell it from most of the other normal molecules because then the two molecules smack and form a dimer of each other, you will tend to have a molecular mass that is double than expected. And questions tend to hint out to you that, for example, the molecular mass is double, or what could be a reason for this interaction? Well, because it's because of dimerization, right? So in general, you can have like hydrogen bonding, or you could have dative bonds that form between the two molecules. And these are stable enough to make the molecule combine and into and form a dimer. So example is AlCl3. So my Al over here is electron deficient, and because of that, it can acquire 2 electrons, and lo and behold, the almighty dative bond has shown itself, right? So this is where dative bonds are important. The chlorine from another molecule will just do a dative bond. So you can see that I represent these. These are the dative bonds, right? And remember, the strength of my dative bond is equivalent to a covalent bond. So, and bonds are strong, they're not easy to break. So this tends to be quite stable. And another example is ethanoic acid. So it's not just dative bonds, you can also use hydrogen bonding to have the bonding and the dimerization of my molecules itself. Alright, next up is talking about intramolecular versus intermolecular forces. So intramolecular, as the name suggests, is within the molecule. And intermolecular, also as the name suggests, it is across or between different molecules. Right, and if you do a comparison, right, intermolecular forces tend to be more extensive, of course, because you can branch out more. You're not limited to just your own molecule itself compared to this intramolecular forces, right? And because of that, your intermolecular forces tend to have a higher, if a molecule is capable of intermolecular forces, it tends to have a higher BP than something that's intramolecular forces. And for solubility wise, if you're talking about solubility in water, for example, your intermolecular forces are, those capable of intermolecular forces are more soluble because they can interact with the solvent molecules, like water molecules, for example. This big molecule over here, you don't have to worry about the name, right? But this is just an example of the intermolecular force versus the intramolecular force, right? And they love to ask about intramolecular forces, right? Because students don't really see, or they cannot picture that the intramolecular force is happening. Next up, we're moving on to giant molecular structures. Finally, away from simple molecular structures. So giant molecular structures, some examples are like your diamond, your graphite, your silicon dioxide, and actually there's also like boron nitride, for example, right? So diamond tends to have this structure over here. So we know that the main force, right, the main bond is the strong covalent bonds, right? And we know that covalent bonds are very strong. You need a lot of energy, so they tend to have high melting point and boiling point. And they are non-conductors of electricity because, very similar to simple molecular structures, they have electrons localized in your covalent bonds. Again, remember this explanation. It tends to come out a lot. And then it's very insoluble and polar, in polar and non-polar solvents. Well, it's kind of expected. Just think about your diamond. If diamonds are so easily soluble, that would be a problem, right? So your covalent bonds are just too strong, so you cannot compensate for the energy to break the covalent bonds, right? So you have no interaction that can compensate this, so it's generally not very soluble. And of course, it is hard, strong, and very non-malleable because it's diamond, or it's a giant molecular structure. The covalent bonds are too strong. Special cases of giant molecular structures, another structure itself within that is graphite. So graphite is this special structure where you have layers of atoms that is held together by strong covalent bonds. So you can see these hexagonal rings, right? And each like dot over here, if I can point out one over here, this is like a carbon atom. And usually carbon would have 4 bonds, as you can see with diamond, but in graphite they only have 3 bonds. And that's just the amazing thing about graphite, is that a very stable structure comes out of it. Actually, it is just called an allotrope, right? Because graphite is also carbon and diamond is also carbon, but they have very different structures. And this allotrope of carbon itself, right, it forms 3 bonds, right? So do take note of this structure because they love to ask, and you have to be able to explain the structure. So there's 3 other carbon atoms, and they go by strong covalent bonds, and they create these layers of carbon. And these layers of carbon, right, each carbon atom has 1 extra electron, and this electron tends to be delocalized. And because of that, you have these huge electron clouds, right? So you can imagine this is like a huge electron cloud, this whole layer, right? And this also has a huge layer. And because of that, when you have electron clouds, what does that mean? You get ID-ID. So this interaction over here is actually ID-ID between the electron clouds. Now, how does this translate to some special properties? Well, aside from the fact that it has very high melting points and boiling points, because obviously the core of its structure is the covalent bonds. It also is especially a conductor of electricity, and this is because, right, we talked about that delocalized electron, right, and because these electrons are delocalized, they can act as mobile charge carriers, right? They receive the energy and then they can just pass the charge on and on and on, and that's how generally electricity is conducted. And they tend to be soft and slippery. So this is because of the weak ID-ID between the layers, right? So you can actually have the layers shifting over each other like this, right? And it look like I'm dancing, but then because of that, right, it's really often used as a lubricant. Okay, and it's also a good lubricant because actually it has a high melting point and boiling point, which helps in oiling up or lubricating your machines that tend to heat up easily. Now we move on to ionic bonding. So ionic bonding, right, this main structure is this giant ionic lattice. So you always say that like sodium chloride exists as a giant ionic lattice with the main force is strong electrostatic forces of attraction between my sodium ions and my chloride ions. Realize how I name my ions? Yep, please do this in your answer. Right, and just to help you visualize, right, from the dot and cross diagram of sodium chloride, where just take note that you don't have to, no need to draw the valence electron here, because actually the one valence electron in sodium is given away to the chlorine. And while it might look simple between the two ions, but actually the whole lattice structure is made of like oppositely charged ions that alternate between each other, and it can form very, very complex structures, as you can see over here. And this is just one tiny cube. So can you imagine like a whole system of like maybe 1 million cubes of this? This is like, there would probably be a very huge like sodium chloride chunk. And the factors that affect my strength of my ionic bond, right, is if you look at, you have to look at the lattice energy. And what is lattice energy? Yes, memorize this definition. Memorize this. I don't ask for memorizing that much, but you have to memorize these things. So lattice energy is the energy formed when 1 mole of solid ionic compound is formed from its constituent gaseous ions. Again, the states matter, right? And this is taught more in chemical energetics, but we'll talk more about that in chemical energetics. So all you need to know now is that lattice energy is dependent mainly on the Q and the R. So Q is the charge of my ions. So you realize there's a plus and there's a minus, because plus is for cations and minus for anions. And then R is the radius. Right? In essence, I'm looking at the charge density of both the ions. Also realize that this is a x, not x, but like a multiplying function over a plus function at the bottom, which means that your charge actually has a higher effect than radius for lattice energy, right? Now, what are some properties of ionic bonding? Well, of course, the electrostatic forces of attraction are very strong, so your ionic bond has to be very strong, right? And because of that, also, they are very strong and hard, right? But they're also very brittle. A very key thing about ionic structures, right? Just think of it like looking at this diagram where you have oppositely charged ions in this little structure, and when you put stress on it, right, and you manage to shift all the ions by like 1 row, very simplified example over here, you have these repulsions, and because of that, the whole molecule would just break apart, right? So these repulsions would cause it to break apart, right? So ionic compounds tend to be very brittle. And they also tend to be non-conductors of electricity in general, right? Because your ions are in fixed positions, they because the electrostatic forces of attraction are so strong, they're in fixed positions, so they can't really act as mobile charge carriers. But when you melt them down or you dissolve them, right, basically in the molten or aqueous state, these ions tend to be more mobile, right? Because you have already inserted energy to like overcome the interaction, the strong electrostatic forces of attraction. So these ions become mobile enough that they can conduct electricity. They tend to be soluble in polar solvents, right? And this is because they form these favorable ion-dipole interactions. This is commonly tested as well, do take note. So what are ion-dipole interactions? It's basically this interaction over here where like your cation in a very polar solvent, the delta minus in the polar molecule, so for example this O's over here, so these O's, right, would gravitate towards the plus ion, and this is very favorable because the delta minus is a partial negative charge, right? It's going towards the positive charge cation. And then for anion, the positively charged parts of the solvent, for example the hydrogens in water, they will go towards the negative ion. Alright, next we look at some differences in character in covalent bonding or ionic bonding. So when your atoms have considerable electronegativity difference, right, you actually get partial charges that create a dipole in your covalent bond. And these help to strengthen your covalent bond, as I mentioned earlier in the lecture itself. It's kind of represented in this over here. Okay, and versus, I'll go up to that in a minute, when you have covalent character in an ionic bond, right? Ionic bonds can have covalent characters itself. And this is demonstrated due to my polarization. I'm actually distorting the anion electron cloud, right? And because of that, there is some form of like electron sharing. It's not much, but there is some electron sharing, right? And these factors are due to, yes, do take note of this, it's very likely to be asked. So when you have a high positive charge on your cation tends to be very small. So we look at the radius. And then we look at the anion radius is very huge, right? And these factors all make it such that there is high polarization. Of course, when there's low polarization, you look at the opposite. All right, now lastly is metallic bonding. So metallic bonding, the structure itself is a giant metallic lattice. Right, so for example, sodium exists as a giant metallic lattice with strong electrostatic forces of attraction between my metal cation and the sea of delocalized electrons. So take note of this delocalized electrons, right? So a very typical representation is when you have all these cations, for example, sodium cations, right? And they each lose one electron, and all these electrons are like in a pool, this sea of delocalized electrons. They don't really belong to any cation in particular. They're just kind of shared between or amongst each other. And the factors affecting the strength of my metallic bond is the charge density, right? Right, in general, right, if you have more electrons that you lose, right, the charge is higher. And if the charge is higher, you can imagine it's like a stronger magnet. So your electrostatic forces of attractions are just stronger, right? Again, this is the charge. And then the other one is the radius, right? So if my radius is bigger, right, it means the charge density is smaller. In general, if my radius is bigger, it means my charge isn't really that strong. It's more diffused. It's not that like located or concentrated, I would say. And then we look at properties of metals. So metals also tend to have very high melting point and boiling point. Okay, looking at electrostatic forces of attraction. Okay, but just take note, this is lower. This tends to be lower than ionic compounds. Right, and they are, of course, metals, they are very good conductors of electricity, right? Because of this sea of delocalized electrons, right? And they all act as mobile charge carriers. Okay, they're also malleable and ductile. Okay, because if you look at the structure, right, these layers of cations, they very easily move, right? Because they're all uniformly shaped. Like if you apply stress to, like, let's say the left, they would just willingly just shift. So they are very malleable, they are very ductile, right? And they also form alloys. So alloys are basically mixture of two different like metal cations or types, or it can be 2 or 3 or maybe even more types of metal cations. And because of that, you actually make the material harder and stronger. Because if you look over here, in blue is like one metal ion and in red is another metal ion. The structure tends to be a bit distorted, right? It's not like layers that can slide past each other very easily, right? So if you apply a stress over here, it's not going to be easy to shift the atoms, the ions, right? So when you form your alloys, you tend to make a material that is harder and stronger, but of course, it also means that it's less malleable and ductile. So that's all for chemical bonding. Now, if you want to learn more from me, do remember to hit the subscribe button. And if you want to join in on the online lessons, feel free to click the link below and book a call with me, and I'll be able to schedule some time to go through with you your past exam paper and perhaps the difficulties and challenges and any other clarifications you might have about the online lessons. I'll see y'all in the next lesson.